Hey guys, so today we're going to be going over carboxylic acid derivatives. We introduced it a bit last time, but now we're going to be going over more of their properties as well as the reactions that are associated with them. So up here I drew a carboxylic acid, and if I take out this red OH and replace it with either an amine to form an amide, an alcohol which forms an ester, an acetyl group which forms an anhydride, or a halogen which forms an acyl halide, you can get a carboxylic acid derivative. So these are the four main ones you guys will see through your course, so they'll be coming up again. We use them a lot of times in reactions, and they work as electrophiles because this blue carbon in each one of these has a slight positive charge on it. And because it's an electrophile, it reacts with the nucleophile to create a product. We can rank these four carboxylic acid derivatives in terms of increasing or decreasing reaction speeds. So here I drew an energy diagram, which is really important for us to understand how our derivatives work. We start off with our reactants, denoted by R. You have your transition state, and then you eventually get your products. Your reactants in this case would be your derivative, but remember, our derivative acts as an electrophile, so it's going to react with a nucleophile. And our products, which is just going to be the product of this reaction. So now the main thing we want to worry about here is delta G. Delta G is the difference in energy between our reactants and our products. And in order for something to be very reactive, we want to maximize this. We want to think of it sort of like a roller coaster. Or like a child will want to go on the roller coaster that has the biggest sort of drop, right? So if I have a roller coaster like this versus one that's like this, obviously this one's more favorable and it's going to have a bigger line, more kids want to get on it. It's the same thing here. If I have a derivative that has this energy diagram, it's going to be much more reactive, much better, and we want to use it more synthetically. So there's a way to figure out which one is this and which one is that. And it's based on two factors, because we want to make this difference between the reactants and the products the greatest. So we want to shift up the reactants and we want to bring down the products. In other words, we want to make the reactants more unstable and the products more stable. So let's look at the first criteria, which is making the reactant more unstable. So let's look at what the reaction looks like. So we have our carboxylic acid derivative here. R can be whatever that we did above, and we have a nucleophile. Our nucleophile is going to attack this electrophilic center, push up the pi bond, and what that's going to give us is a tetrahedral intermediate. So this is our tetrahedral intermediate. In order for this reaction to proceed, we need a good electrophile and a good nucleophile. So to make this a good electrophile, we want to maximize the positive charge that's on this carbon right here. So let's take a look at our four carboxylic acid derivatives. Let's use yellow. So with our NH2, we know that it donates some electron density through resonance. Our OH also donates electron density to the center through resonance, about the same amount. However, if we look at this oxygen over here, it doesn't donate as much. The reason being, it can donate both to the left and to the right. So it can donate this way or this way. And because it can do like 50% this way and 50% that way, you're cutting that stream in half. So you're only getting like 50% of the electron donation as we want. And here, our chloride can also donate electron density through resonance. So it's about the same right now, but the breaking factor is induction. I guess we have to use brown, purple. Let's use orange. So our NH2, our nitrogen, is pretty electronegative, but not compared to the rest of these atoms. So let's say the induction only works a little bit like this, because it's pulling the electrons towards the electronegative nitrogen, because it's more electronegative than carbon. Our oxygen is a bit more electronegative than our nitrogen. so its induction arrow is going to be a little bit bigger. Here, our oxygen is the same amount, so we keep that induction arrow about the same. But our chlorine is ridiculously electronegative, so it's much more withdrawing. So in reality, our amide over here, it donates the most density, while our acyl chloride withdraws the most. That's why our amide is a strongly activating group, while our acyl chloride is a weakly deactivating group. So remember, we want to make this carboxylic acid derivative the most reactive possible. That means we need to put a positive charge on there. And the way we do that is we want to withdraw the most. So our acyl chloride wins in that factor. So if we draw an arrow going this way, we know it's going to be the most reactive. Reason being because there's a larger positive charge on this carbon right here. The other factor we have to look at is the products. So let's go back to the initial energy diagram we drew. So we looked at the first factor, which is basically pushing up this reactance line. And we did that because we know we have to increase the positive charge here. Now the second factor is we have to push down this products line. So before we left off at our tetrahedral intermediate, our nucleophile came in, attacked our carboxylic acid derivative, and pushed up the pi bond. Now there's two ways that we can proceed. The first one is that this O- just grabs a proton. So what you're going to get is this. So this product, it would be called your addition protonation product because you add your nucleophile here and then you protonate your O-. Addition protonation. However, the other way that this reaction can proceed, let's just erase this. Is this O- can push down electron density and it can kick off this R group. So what you're going to get there would be something that looks like this. So this one wouldn't be called your addition protonation. Here we're eliminating. So this would be your addition elimination product. This is the one we're now going to be more interested in, and we'll see why. However, the one thing we have to know is that there's two ways that this reaction can proceed. It wants to favor the one on the right. The reason why is because you're creating a double bond with oxygen, and that's very stabilizing. So this one is more favorable in terms of enthalpy. However, we can't always do this type of reaction, and we'll see the caveats to it later. So let's take two examples of carbonyls. The first one is acetone, second one is acyl chloride. We're going to add just a random nucleophile to it, and we're going to see, does it proceed via the addition elimination route, or does it proceed via addition protonation? So the first step is your nucleophile is going to come in and attack the electrophilic center, and it's going to push up the pi bond in both of them. And we have our nucleophile sticking out on the top over here. So now, just for kicks, this might ring a few red flags to some of you guys if you've seen this around, but I'm going to do your addition elimination with this one just to see hypothetically what would happen. So our O- is going to come down and it's going to push off one of these methyl groups. If we look at this once acyl chloride, same thing's going to happen. But instead, we're going to push off this chloride. So what we should end up getting is something that looks like this. Our nucleophile stays on because we just added it, so it wants to be part of our product. And here, our Cl becomes a minus. So it's going to be floating around in solution just like this. While in solution for the first one, our CH3 turns into CH3 minus because it accepts that bond. So we're going to get this. So for those of you who have seen this type of reaction before, you've known that the second one happens. But our first one, in reality, it doesn't happen. This is not a valid reaction. This is actually incorrect. And the reason why is we can tell from our reaction coordinate diagrams. So let's do our second one first. So we start off with our reactants, and then we have a transition state. This is our transition state. This is the tetrahedral intermediate. And now our products. Our products are going to be much lower. So this is good. This means the reaction will proceed, because if we look at the difference between our reactants and products, there's a negative amount. So this is your G, and it's negative. Now if we look at the top reaction, you start off with the reactants again. You have your tetrahedral intermediate, but now your products isn't very low. What's going to happen is it's going to skyrocket, and you're going to get something like that. Now if you look at it, you have a positive delta G. And if you guys remember from Gen Chem, you want a negative delta G in order for a reaction to proceed. You want to fall down the roller coaster. You don't want to have to climb up it, right? So the next question you guys might have is, how come there's such a big difference? Everything stays the same here except for the products. And let's look at the products here. Well, these two are pretty much the same. They're exactly the same, so that's not where the difference lies. It lies in the thing you've created on the side, your byproduct. Here you create CH3 minus, and here you create Cl minus. Both of these, they're not great. Reason being, you have a negative charge on them. But one of them is much better than the other. Remember, let's go back to our initial reaction coordinate diagram over here. We want to push up the reactants and push down the products to create the biggest roller coaster possible. If we push down our products, that means we're going to create the most stable thing possible. That means here we've created something more stable than this. Stability means you don't want to react. So if we create a stable product, that means it's not reactive. So how do we tell? How is Cl minus not reactive compared to CH3 minus? We can look at their pKa's. Here, our Cl minus, its conjugate acid is hydrochloric acid, which has a pK of -7. That means it's a ridiculously good acid. However, we know that strong acids have weak conjugate bases. That was the rule we always learned. So because its conjugate acid is so strong, Cl minus will be a very stable base. And that's good because it's not reactive, so it pushes down our products in terms of energy. Let's look at our CH3 minus. Our CH3 minus, its conjugate acid is CH4, methyl. And if you look at that, it has a pK of about 40 to 50. That means that it's not acidic at all, which means its conjugate base is much more unstable. Also, if you just think pragmatically, you know that CH4 is a pretty inert type of molecule. If you take away a proton from it, you're going to make it very unstable. However, if HCl, you know HCl is very reactive, so if you take away a proton, it's going to make it less reactive. And this negative charge, we know electronegative atoms stabilize negative charge better, so this is more stabilized. And that's part of the reason why this reaction goes forward and this one doesn't. So let's look at all the carboxylic acid derivatives we have and apply this type of stuff. So here, if I do an addition elimination reaction, what will come off? We'll have an NH2 minus come off. If I do addition elimination here, we have this come off. This we have our, well, you guys should remember this from the last video, this is our carboxylate anion. And here we just have our chloride come off. So in order to assess we want to figure out which one of these is the most stable. We can't do that looking at the bases. It's not that easy. So let's convert it to its conjugate acid first. So the conjugate acid, you just add on a proton and add one charge. So you add one proton and you make this neutral. So you're going to get NH3 here. You're going to get ethanol here, acetic acid, oops, and you're going to get hydrochloric acid here. So let's assign the pKa's of these. You guys should know the pKa chart by memory now, but just in case you don't, let's go through it. For NH3, it's about 33. For ethanol, it's about 15 to 16. Acetic acid, you guys should remember this from the last video, it's about 4, it's a weak acid. And hydrochloric acid is a very strong acid, so it's negative 7. Remember, the trend is lower pKa, more acidic. So if we use this rule, we know that with these conjugate acids, HCl is more acidic. Right? And this guy's not that acidic. So if we look at our conjugate base, that means we know that the more acidic something is, the more stable the conjugate base. So that means this way we're increasing in stability. And remember, from our reaction coordinate diagram, our RC diagram, we want to push up our reactants and pull down our products to create this biggest roller coaster possible. And part of pushing down that products is we want to create the most stable thing. So here, Cl- is the most stable side product you can create. NH2- is not. It's a very good base. That's why when we have those reactions like this, and then we add in like a chloride and then NaNH2, it'll do elimination because it acts as a very good base. We don't want that. We want something that will just stay where it is and not react. So our Cl- provides us that. And that's why acyl chloride is more reactive. So let's look at all those factors we just examined. The first one was we want to look at the reactants. If we have our RC diagram, we have our reactants up here and our products. To make something more reactive, we want to make it bigger, right? We want the fall to be larger. So we want to push up our reactants and pull down our products. So to push up our reactants, we want something to be more unstable. And we know that this acyl chloride is more unstable because it has this very big induction force. So you're going to increase the positive charge on this electrophilic carbon. And remember, charges are unstable inherently. Now if we look at our products, we know we want to push down the products in terms of energy. We want to make it more stable. And the way we do that is we look at the leaving group that we kick off. We know chloride minus Cl minus is a very stable base, and that'll allow this product to be pushed down. Whereas opposed if we form NH2-, that'll be very bad. It's too reactive, and it's going to go the other way. So those are the factors going into carboxylic acid derivative stability and reaction rates. Whoops. So now let's go into some of the reactions and things like that. So here I organized our derivatives in terms of increasing energy. So we have our chlorides at the top and our amide at the bottom. I shifted it from horizontal to vertical like this because it's important to see the concepts of energy. From our RC diagram, we know we always go from something of high energy to something of low energy. So that means we go from something up here to down here, and that works pretty easily. So that's why if I want to create an anhydride from an acyl chloride, I just need to add acetic acid. If I want to create an ester from our acyl chloride, I just need to add alcohol. And if I want to create an amide from our acyl chloride, I just have to add some amine. I'll get into why there's 2 later. That's not that important right now. But you see that the reaction sort of makes sense here. We're adding an acyl group, so we add an acetyl. Here there's an alcohol, so you add an alcohol. Everything makes sense. And in addition, this is an ester right here. Esters are about the same energy as the carboxylic acid, so I'm going to draw that over here, hypothetically. So if I want to form this carboxylic acid from an acyl chloride, I can, because we're going from something high energy to low energy. And what do you think we can add? Well, since there's such a large gap, we can just add water. So we'll go to form this, we'll just add water. But now let's say I want to form an acyl chloride from a carboxylic acid. So why can't I do something like this? If I start with the carboxylic acid, why can't I just add Cl minus and create an acyl chloride? The reason why is because there's too much energy you have to climb up. It's just not favorable enough. So you need a specialized sort of reagent. And we have one, and if you guys remember, that one is your SOCl2. So it doesn't work like a normal nucleophile. It's stronger, and there's a specialized mechanism for it. But that's the reason why we can't just use Cl minus, because you have to climb up the ladder. You want to fall down it, and that's why that's like the trend of the reactions we'll see today. So let's examine one of them. Let's go from our highest energy to our lowest energy. So we're going from our acyl chloride to our amide. So remember before I told you guys don't worry about the 2 moles of NH3 that I put up over here. So now you guys will kind of understand why we do that. It's just specialized for this one reaction only. So we know that this is an electrophilic center and this is a nucleophile, so it's going to attack. What you're going to end up getting is something like this. Oh crap, I forgot to push up the pi bond. So this is our tetrahedral intermediate, and we also have a positive charge on this amine. So now we want to keep this amine here. We just add it in, and we know we have to deprotonate things we want to keep. So what's going to deprotonate it? Well, if we go back to that acid-base chart I put up over here, remember our NH2 has a high pKa, and high pKa indicates good basicity. So instead of water, your NH2 or NH3 will actually be doing the deprotonation of this, which is why you need that second mole of it. So let's draw it. Let's draw it in. NH2. It's going to come in, and it's going to deprotonate this and kick it off. So we should see something like this. And now our O minus can come down, form a pi bond, and kick off our chloride. So we should be left with this. We formed an amide. So it's a pretty simple reaction. Electrophile, nucleophile comes in, deprotonate it, and then you can just addition and eliminate. So now the other reactions I want to go over are your ester hydrolysis. That's basically taking this ester over here and making it go towards the carboxylic acid. So you need to catalyze this reaction because there's no real gain in energy. The reason why is because they're at the same energy level, so it's not really favorable. To make it more favorable, you have to add in either acid or base, both of which will do the catalysis job. So let's take our acid catalyzed first. This is the mechanism you guys will most likely see on your exam, so please know this one or pay attention very carefully. So let's just take a methyl ester. And now let's say we have, oh, whoops. The first step whenever you're in acid is you want to protonate. So your methyl ester will grab this proton. You're going to get a positive charge on this oxygen. And remember, whenever you protonate a carbonyl, you create a better electrophile. So now this guy is more susceptible to nucleophilic attack. And that's exactly what's going to happen now. So we have our water, which is an alright nucleophile. It's going to come in, and it's going to attack this electrophilic center and push up that pi bond. And we should get something like this. This is a H. So now let's think. We want to create a carboxylic acid. That's the end goal. We're hydrolyzing this ester to form COOH. We know we need this in our final molecule. So if we want to keep it, we have to deprotonate it. So we're going to use some water that's floating around in solution. And we're going to deprotonate this oxonium ion. Now, we're pretty close, sort of, to getting a carboxylic acid, but we know we can't have this guy here. There's no methyl sticking off in oxygen. So we need to eliminate this. However, this one, if we eliminate it right now, it'll be a great base, and that's very unstable. So we need to somehow nullify that. And the way we do that is we protonate it. Whatever we want to kick off, we have to protonate it first. So there's going to be some H plus in solution because we're working with acid catalysis, and this is going to grab it. Cool. So now we created a good leaving group. So now one of our OHs, it doesn't matter. They're both identical. They're going to come with their electrons and kick off this good leaving group. So we're left with CH3OH. Methanol is our byproduct. But we're almost there. We need one last step, and that is just to deprotonate this. So we're just going to have some probably water floating around in solution. And that water is going to take off this proton and kick this off. So we should be left with a carboxylic acid. So this is a pretty long mechanism, as you guys see. It's 6 steps. When I told you about the formation of an ester through Fischer esterification in our last video, I gave you an acronym, PAD-PED. It helped you guys sort of memorize it. It's the same acronym here, actually. You protonate your carbonyl, then you add in your nucleophile, deprotonate this group, protonate again, eliminate, and then deprotonate. So PAD-PED is the sort of mnemonic you can use to learn ester hydrolysis for the acid catalyzed way. But it's good always to learn how to think through the steps first. The other one we have to go over is the base catalyzed mechanism. So let's start off with our methyl ester again. Now what's going to happen is, let's say I have an OH minus now in solution. So there's no protonation anymore. We can't do that. We're working in basic conditions. So now this guy is just going to have to attack. This is a pretty slow step because there's no, remember this protonation created a good electrophile and that sped it up. Here there's no protonation. So it's a bit slower, but still works. And you should get something like this. Now, we don't want this CH3O group sticking off here. So we're going to kick it off using our anion. This is what was kicked off from here. And then we have this carboxylic acid. But wait, we're not done yet. Even though we have our acid, it looks like we're finished. Remember, we're working in basic conditions. And this is still a carboxylic acid. So it's going to deprotonate itself. And I believe it's not going to be OH minus that does it. It's going to be your OR minus. And it's going to take its negative charge and pluck off this proton. So now you'll be left with a carboxylate anion. And this last step actually is irreversible because you're forming a carboxylate salt. So there's no equilibrium arrows here. Now it's just going to be irreversible. So this step is irreversible. The base catalyzed is irreversible, not the acid catalyzed. So another name for base catalyzed ester hydrolysis is saponification. Base catalyzed ester hydrolysis is also known as saponification. And it's a pretty cool name. I guess it's better than saying the base catalyzed ester hydrolysis. But it's also pretty synthetically useful, and it's good at getting rid of ester groups. So let's say I pose this problem to you guys right here. I have this really complex group, which when you look at it, it's just an ester functional group with phenol. And I ask you to synthesize CH4, just methyl. How are you going to do that? There's no one step. It's a three-step mechanism, and you can use the acronym SAD. The S stands for saponification, the A stands for acidification, and the D is for decarboxylation. All three of these reactions you guys have seen before, and I'm pretty sure it might show up on your exam. So let's just pay attention to this one. So to saponify something, let's jog our memory again what it was. We take an ester, add base to it, and you're going to get a carboxylate anion. So if we have our ester, we're going to add base to it. So let's add that into our reagents. So NaOH. That's our base, and that's going to cleave off the rest of this stuff. So what we're going to be left with is this. Saponification cleaves off all of this. We're not really interested in it anymore. So now we have our carboxylate salt. And the next step is A, which is acidify. This is just the same thing as an acid workup. You guys have seen this before. So just add H3O+, and you're going to form your carboxylic acid again. And now lastly, you're going to have to turn your carboxylic acid into a CH4. This is a reaction you guys have seen from the last video. This is decarboxylation. Decarboxylation only works in heat. Well, for that you would also need another ketone. So I guess that problem was a bit botched. If you had to form, I guess, this from here, you can decarboxylate it and you would be left with just this aldehyde. So the main principle is I want you guys to memorize SAD. SAD is saponify, acidification, and then decarboxylation. So SAD is just a way of removing ester groups. So from here to here, it's pretty much the same, except this red got removed. This red is just an ester. So this is pretty useful synthetically. And then the last reaction I sort of want to go over is our nitriles. So from our last video, you guys remember nitriles were a great way to create carboxylic acids. You start with an electrophile, you can do your SN2 reaction and add in a cyanide. If you add an acid, the cyanide will turn into a carboxylic acid. This is stuff we've seen before. But in our new set of lecture notes, you guys were introduced to the fact that the intermediate here is an amide. And it's pretty important because they might ask you like a synthesis question on this or how this happens. So I'm going to go through the steps of how to synthesize carboxylic acid from CN. Because first of all, it seems pretty interesting, just like how do you change up the N to an O? It's just a lot of steps. So let's go through it step by step. So you can do this reaction in either acid or base. I'm going to use base because it's a bit simpler and that's the one that tends to show up more in exams. So if we have our OH minus and our CN group, the rest of this is just R. Our OH minus is going to attack the electrophile and push up this pi bond. So you should get this. Now you have two sets of lone pairs on this nitrogen, and you have an OH. Now this negative charge is going to be reduced by getting a proton from solution. So now we have only one lone pair remaining on the nitrogen. So now somehow we have to get from this stage to an amide. This next reaction you guys have seen before, it's just tautomerization. For example, when we had our enol and we tautomerize it, what do we end up getting? We just get this. So you just shift the double bond over and get rid of this hydrogen. Shift the double bond over, get rid of this hydrogen, and we get an amide. The mechanism for that is you still have OH minus floating in solution. So now there's going to be a concerted step. There's also a little bit of water floating in solution. This OH minus will deprotonate this hydrogen. This bond will fall off here. This guy will fall off onto the nitrogen, and this lone pair will grab this proton. It's a lot of steps, but in reality, if you just think tautomerization, you can work this one out. So now you have an NH2, and you formed a carbonyl group. So this is the intermediate of our reaction. And sometimes they might ask you, oh, what's the intermediate of acid catalyzed cyanide hydrolysis? And you can say it confidently, it's an amide, and you can work through these steps. So now we're not done yet because somehow we have to get from this amide to the carboxylic acid. So now there's sort of the second part of this reaction. So I'll go through that with you guys. So now the first thing that's going to happen is you're going to have to do nucleophilic addition because we have an electrophile. So you're going to attack the electrophilic center and push up this pi bond. Oh, that looked bad. That's not even legible. NH2. And there's an OH here that we just added in. So now, before we kick anything off, this is the weird part of the mechanism. You have to create a dianion. So I'll write this over here. Dianion. So the way we do that is we have to deprotonate this other OH. So you take off this hydrogen, it falls back. Oh, it's a little too far. So here you should be left with two anions. I asked my professor about why this reaction happens like this. It seems rather odd. And the reason why is because your amide is very stable, so you want to increase the instability of the intermediate, so that way it proceeds. So now you're increasing because you have two negative charges in close proximity. The last thing is now you have a leaving group, but it's a pretty crappy leaving group, right? Because it's a good base. So now we have to protonate it so we can kick it off. So it's going to grab an H plus just floating in solution. So now you're going to get this. So now you have a total of 3 charges here. This is really bad. Now it has to do something to get rid of it. You're going to do your elimination now. It's going to kick off this nitrogen. And what we're going to be left with is our carboxylate anion. And then you have an NH3 in solution. So this is like the 7-step mechanism about how you could create a carboxylic acid from a nitrile using just base. This is the one, she covered it pretty intensively in her notes, so it's just pay attention to it. Alright, so next up, I kind of got confused when I looked at the lecture notes for the class because it just seemed like a lot of reactions, and I know it might feel the same way for you guys. So I created this chart, and I feel if you know this chart pretty well, you're set for this week's lecture notes. This is all you really need. So let's go through it step by step. So on the top row, we have our carboxylic acid derivatives, and on our left side, we have our nucleophiles or whatever reagents, and we're going to get our reaction somewhere. Not all of the boxes are filled, just because they're not always like reactions they're going to test. I'm going to zoom out so you guys can take a picture of it because I feel like this is pretty important for you guys to know. So quickly, if you can take a screenshot or a picture, and then we can resume. So first off, we have our acyl chloride. If we have our organometallic Grignard reagent come, it's going to attack it twice and form an alcohol. The same sort of reaction happens with both with the acyl chloride and the ester. We don't worry about it too much with our amide because our amide is a very bad electrophile. We established this in the first part of the video, and it attacks this cyanide to form a ketone. So these are 3 very weird products that we don't initially expect. So let's go into more about why it happens. First off, why does the Grignard attack acyl chlorides and esters twice? So the mechanism is the same for both, so I'll just show it to you for acyl chloride. So we have our CH3 MgBr, which is just a carbon ion. It's going to come in, attack this electrophilic center. It's going to push up the pi bond. So what we should get is something that looks like this. We're going to get our tetrahedral intermediate. Now we have our CH3 that we just added on. So now, let's go back to the very first thing I drew up here. So a nucleophile can add in, and you're going to get your tetrahedral intermediate. Then it has 2 options. It can either addition protonate or addition eliminate. This is more favorable because you create your C double bond O, but it doesn't always happen based on whether or not this is a good base or a weak base. Weak bases allow this to happen, which is why acyl chlorides proceed, because Cl- is a weak base. So now let's, where were we? Further down. So now we were over here. We created our O-, so we have 2 options. Either we can protonate or we can eliminate. Well, if we eliminate, we can eliminate our chloride, and the reaction would be pretty good because chloride's a weak base. So let's allow that to happen. So you created your acetone, and you have Cl- on the side. But now, let's hold up. We also still have some Grignards floating around in solution. Can it attack it a second time? The answer is yes, because you still have a ketone. So it's going to attack it. But now, when you form our tetrahedral intermediate, it's going to look like this. O-, CH3 we just added on, and another CH3. There's nothing to kick off. If you kick one of these off, you're going to form CH3-, a very good base. We only kick off weak bases, right? So it has to stay like this, and it just has to grab a proton. So you're going to form a tertiary alcohol. So that's what happens with acyl chlorides and esters. They can addition and eliminate the first time, which is why your Grignards can attack it twice. That's why there's 2 green ethyls on each one, because the Grignard from here attacked both of these twice. Now, the cyanide one is just completely different. It's pretty interesting. So let's figure out how that one happens. So the first step, as usual, you're going to attack your electrophilic carbon. So you're going to come in, attack this carbon, and then kick off this pi bond. So what you should get is something that looks like this. This nitrogen will have a minus charge, and you're going to have your CH3 just sticking off here. This minus charge is not favorable, so what's going to happen is this nitrogen is just going to grab a proton. So you're going to end up looking, I'm going to reorient the way this is drawn, because it'll make the next step easier. So this nitrogen that previously had a negative charge is just going to grab a proton, and it'll look like this. So now if you guys are paying attention during ketone and aldehyde chemistry, you guys would know that this is called a imine. And we know that imines can be hydrolyzed back to their ketone form in acid. And anytime we use an organometallic, we always have an acid workup. So for here, it would just be an acid workup to protonate these OHs. But for our cyanide, it wouldn't just act as a workup. It would hydrolyze this imine back to a carbonyl. The mechanism for this, it's a few steps. I'll show like a rudimentary mech. Your OH2 is going to come in, your water is going to come in and attack it and push it up. So you're going to get something like this. And then once you deprotonate, you just have an OH. Protonate this NH2 so you get a good leaving group. And then you can kick it off. And then you should be left with this. And NH2 you just kicked off. NH3 I guess because you something, whatever. And now once you have this, you can deprotonate this hydrogen and you're left with your ketone. So that was just like a very simple mechanism of how you get from an imine to a carbonyl using acid. So just to summarize, your organometallic will attack your cyanide once, and then your acid hydrolysis will convert the imine you just formed into a ketone or an aldehyde. So this is a commonly tested one because it's a very unorthodox reaction. So just make sure you guys don't fall into that trap because that's often a trap. All right. So now, let's say we use our Gilman reagent, or other words, organocuprate. It's only going to attack these acyl chlorides or esters only once, and that's just a special property of it. We were never taught why. Just make sure you guys remember that one very niche fact. Again, it's not going to attack this amide because amides aren't that great of an electrophile, and they're not going to test that one. And they usually never test the one on cyanides either, so I'm not going to go over it. Our next reagent is one you guys just got introduced to. It's called DIBALH. DIBALH, you guys have never seen it before, so I'm going to show you what it looks like. It looks like this. So it's di-isobutyl aluminum something hydride. It has 2 very big bulky groups sticking off, and it has 1 hydrogen. So the main thing to note here is it's a bulky group, and it can only basically deliver 1 hydrogen. Your DIBALH is only used for esters and for cyanides. So let's see how it works. Remember, there are 2 things to remember when we're working with DIBALH. One, from the structure, it's bulky. The other one, it only has 1 H. So let's just write that in here. So if we take our ester, this hydride is going to come in. It's going to attack the electrophilic center once again. And then you're going to get an O- up here. And then you're going to get another O. And you have this hydrogen you just put in. Remember, your ester can do addition elimination. So instead of just protonating, it can kick off this CH3OH. So it's going to do that, and it's going to kick this off. So what we're going to be left with is this. So this is an aldehyde. Okay, cool. Now let's attack again. But wait, remember, our DIBALH only has one hydrogen to give. It already gave this one hydrogen. It can't give any more. And in addition, it's bulky, so it really doesn't want to get up in there again and do another reaction. So it's like a one and done, basically. It's finished. So it reduces an ester down to an aldehyde. Let's see what it does with a cyanide. So with the cyanide, we have our hydride from our DIBALH. It's going to come in, once again, attack our electrophile, and then push up this triple bond, so we get RCH double N. Now we're going to get a minus charge. So once again, this is going to pick up a proton. I'm going to reorient it so it's a little bit easier to see again. So we should get something like this. So once again, pretty similar to what we did up here, you formed an imine. And let's see what our last step of the DIBALH is. We add in H2 and HCl. So for other things, it would just function as a workup. Here, it's not a workup. It reduces our imine to, it doesn't reduce it, sorry. It hydrolyzes it to a ketone, or an aldehyde in this case. So our HCl, or whatever acid it is, will convert our imine to a aldehyde. And I showed you guys the mech up there. It's the same exact mechanism. So that's why with DIBALH, you can only create aldehydes from esters and from cyanides, because it reduces once and it's bulky. Now this one I want you guys to pay attention with, because this one I'm almost sure it'll show up on your exam, because it's a very, very well used trick question. So let's get into it. Our lithium aluminum hydride, it reduces our, let's zoom out. Lithium aluminum hydride, we know it's a great reducing reagent. So it's going to reduce our acyl chloride down to an alcohol, reduces our esters down to an alcohol, but it doesn't reduce our amide down to an alcohol. It reduces it to an amine. That's interesting. We'll see why later. And the last one is it's going to reduce our cyanide down to an amine. That makes sense. It sort of just gets rid of these pi bonds until you're left with a primary amine. So let's figure out how lithium aluminum hydride works on acyl chloride and esters. Those ones made sense. So our hydride from our lithium aluminum hydride is going to come in, attack this electrophilic center, and it's going to push up this pi bond. So you're going to get O minus, this is from before, and you have this H you just added in. Now, remember, esters and acyl chlorides can do addition elimination, so it's going to eliminate this, and you're going to be left with an aldehyde. Okay, but remember, you still have 4 more of these hydrogens, because there's 4 of them attached to each reagent, right? So let's just say another one comes in, and it's going to attack again, because it can attack an aldehyde. And when that happens, you're going to end up getting an O minus, and then the acid workup will convert it to ethanol. So that's how we got those for both acyl chloride and esters. It's the same mechanism. That makes sense. That one you can intuitively derive. Now for amides, it's completely different. This was in my PowerPoints from last year. It wasn't in yours, so I'm thankful you guys don't have to know it because it's ridiculous. But the first step is that your lithium aluminum hydride acts as a base and it deprotonates. This is much different from our initial mech when it just acts as a nucleophile and adds in. So that's like the first step of divergence. And in the end, you're not going to get ethanol, you're going to get some weird thing, and that's going to give you an amine. So please, please, please take note of this one box. I feel like it'll show up on your exam because they like those types of trick questions. So it reduces it down to an amine. It doesn't reduce it down to an alcohol like the rest. So for the last 2 rows, it's H3O plus and OH minus. Those are just intended to be hydrolysis reactions. I'm not going to go into it too much. You just break apart whatever you have. So if I have an ester, I'm going to break it up into a carboxylic acid and an alcohol. And remember, if you take these two and add acid, you get Fischer esterification to regenerate this. So it makes sense. Here, you break it up too. Just make sure you protonate the NH4 plus because NH3 is a good base. So grab that proton to create this. Same thing over here. What's in brackets is just that we had our cyanide. And remember, when we do acid catalyzed cyanide hydrolysis, we create a carboxylic acid. But our intermediate was an amide. And we did that reaction up here. We created our amide, and then we created our carboxylic acid. So just remember where you're coming from. And then for these two, it's the same. Just remember to deprotonate the carboxylic acid if you're working in base. And for acyl chlorides, you don't really need acid or base because it's not very reactive. It's very reactive, so you don't need a catalyst. You just need to add water, and it'll work by itself. And one last thing to note is your acid catalyzed ester hydrolysis mechanism. It showed up on like every other exam previously, so you guys should know it well. I went over it with you on the top, and the acronym is PAD-PED. So just make sure you guys know this mechanism very well. We went over it, so yeah, it's not too bad. Now, the fun part, we're going to have some practice problems. So take a few minutes to try and do these practice problems, and hopefully you guys can get somewhere. Pause the video, and then we'll work through them together. Oh, this one's weird. It didn't. Oh, okay. For this one, you should be rank increasing acidity. So these are your problems. Just take a few seconds to do them, and then we'll jump in soon. Alright, so I hope you guys got a chance to get those problems started. So let's go through the first two. Let's use green. So we know that if we have an ester, this is what this is. This is a cyclic ester. Cyclic esters are called lactones. So this is a lactone. And this is a cyclic amide. This is called a lactam. So you have this hydride over here, and it has this lone pair. It's going to come in, attack this electrophilic center, push up. So we should get something that looks like this O minus here. Right? And remember, esters can do addition elimination. So now this O minus is going to come down and push off this group. So we should be left with, remember, count your carbons because this is an easy way to lose points. 1 carbon, 2 carbon, 3 carbon. So it's 1, 2, 3. A lot of people forget that because they think, oh, it's a square, so it's going to be 4. Just remember it's 1, 2, 3. And then you have, this turns into a carbonyl actually. Let's erase this negative charge now. Oh, I think I messed up. My bad. So sorry, we had 1, 2, 3. So 1, 2, 3, and then another oxygen. And then the oxygen grabs a proton, so it'll end up looking like this. So that's the answer to the first one. What'd you guys get for the second one? A lot of people might say this is the answer. That is incorrect. And remember, I told you guys that's one of those exceptions on the big chart I showed you guys just before, so please take note of that. This one, it basically just reduces the carbonyl without looking at the NH2. So what you're just going to end up getting is this. So despite how similar these guys look, you get completely different products from both of them. So this is a very commonly used trick question, so just keep that in mind, guys. So now here we have 3 reactions. So let's name the reactions so we just get an idea of what they are. First one, we're adding base to an ester. So we're doing base catalyzed ester hydrolysis. What was the cool name of that? That was saponification. So the first one is saponify. Then we're using acid. That's just an acid workup, so that's acidification. Third one, you're just adding heat. That's decarboxylation. This was the SAD acronym I taught you guys from before. And remember, SAD was a great way to get rid of esters. So just from that alone, you guys should know that, oh, we should probably just like lasso out this ester group. But let's just take it step by step. So if I add OH minus and I saponify this, we're going to end up getting this. Cool. Now we have to acidify it, so we're just going to add on a proton. So I'm just going to erase that negative charge and replace it with an H. So you just regenerate a carboxylic acid. So the first 2 steps of SAD, you just turn an ester into a carboxylic acid. And then the last step is decarboxylation. Well, you need a beta diketone for that, right? So are these 2 beta? Well, they have one CH2 group in between, so alpha, beta. So they are. So you can decarboxylate this. So you should get this as your product. This should be your answer. This is a carbonyl, by the way. Alright, so the next one is a rank the acidity problem of your acid derivatives. And this one is a very commonly used question because it's a lot of theory, especially from the first half of the lecture that I talked about. So we want to have the most acidic on the right side, most acidic. And remember, your exam this time is multiple choice, so you'll probably be seeing questions like this. Least acidic on this side. So most acidic means most stable conjugate base, right? And this one means the least stable conjugate base. So we know when we have a dicarbonyl compound, something that looks like this, we're going to have the acidic proton over here. The reason why is then when you take off this proton, you're going to get a carb anion. The anion, we can stabilize it through resonance. So in this case, because it's on this carbon, because it's on this middle carbon here, it can resonate to this carbonyl on the left and to this carbonyl on the right. So it's very stabilizing. So because of that, it stabilizes the conjugate base. So we want our beta dicarbonyls on the right. So we have numbers 2, 4, and 5 are our beta dicarbonyls. So you know those are immediately the most acidic because their conjugate base is resonance stabilized. So 1 and 3 should be in the beginning. So this is 1 and 4. That can't be it. This is 2 and 4. That can't be it. 1 and 3, okay. 4 and 2. And then 1 and 3. Okay, cool. So now we have to sort of break the tie. Remember, if I have an acid, like let's say I take carboxylic acid, what's happening in this reaction is you're taking a base, the base is taking off this proton, and this bond is falling back. If I have something like a fluorine here, it has an induction this way, so it's going to help this bond sort of fall back this way. So it's going to help pull, and it helps in this like tug of war contest. So electron withdrawal increases acidity. So let's draw that. Let's write that. Electron withdrawal increases acidity. So if I look at 1 and 3, we need to break the ties somehow. So we have an OCH3 on this side, and we have this over here. Well, if we remember from our aromatics and stuff like that, we know our OCH3 is actually donating because of resonance, and the induction really doesn't play that much of a role. This is if I put this on a benzene, this would be a strongly activating group, and this would be a weakly activating group, right? So because of that, this one doesn't have withdrawal, it has donation. So this would be the weaker acid. So it should be 1 first and then 3. So because of that, this should be your answer right here. And then you can do the same thing with these guys over here. So this is a trick question. The answer is actually no reaction. The reason why is I want you guys to remember the decarboxylation transition state. You need to get in some sort of hexagonal conformation, and you would end up putting a double bond on this bond, but because it's in this sort of strained ring conformation, you won't be able to. So you can't decarboxylate over here. Here you're adding lithium aluminum hydride onto your cyanide. We know from our table it reduces a cyanide down to an amine. So you should just get something like this, NH2. Alright, for this box problem, now hold up, this one we have to remember, we're working with the nitrile. Our Grignard doesn't attack an alkene, we've learned that in the past. So the first thing it'll do is it's going to attack this nitrile and it's going to push this up, and the nitrogen will grab an H. So our intermediate should look something like this. Carbon, double bond, nitrogen, H, and then we have our phenyl group that we just, oh wait, wrong spot. We have our phenyl group that we just added on. This is an imine, right? So if we add acid to our imine, we're going to do imine hydrolysis. So this is just going to turn into a, what is this? This would be 1, 2, 3, 4. We're going to get something like this. So you're going to turn it into a ketone. So remember that there's always those like trick questions. So here we're working with a diester, and we add NH3. So let's go back to that energy diagram I put up a while back. So here, if we look at this, our esters are over here, while our amide is down here. So it makes sense that our ester wants to drop down here in terms of energy. So what's going to happen is your ester is first going to be attacked by this NH3. So you're going to get this intermediate. NH3. And it's more willing to kick off one of these OMe groups because it would be a weaker base. Because this one has a pKa of about 33, while this guy has a pKa of about 16. Its conjugate acid is more acidic, and therefore its base is weaker, more stable. So we'll kick that off, so you're going to get something that looks like this. So come down, kick this guy off. O-methyl, and then your NH2 group over here. And then afterwards you're going to attack it with another NH3, and then you're going to push it up, it'll come down, it's going to kick off this O-methyl, so you'll be left with this product. And this is our last problem. So once again, we have 3 steps, and if you guys remember from before, this is SAD, saponify, acidify, decarboxylate. So the first step, we have to saponify and acidify. I'm going to class these into one because you're just turning all the esters into carboxylic acids. So you should end up with something like this. So these once previously 3 esters turned into carboxylic acids. That's why there's OHs instead now. Now you have heat, so you can decarboxylate anything that's beta. So let's look at this ketone over here. These guys are alpha, they're not beta, so you can't decarboxylate this guy. However, oh whoops, forgot to put this here. These two can decarboxylate because they're beta to each other, and so can these guys. So let's just like lasso out everything that was here, and we should end up with this as our product. and then 2 CO2s. Remember, it's important that you keep the moles. So yeah, oh whoops. So this is what we covered today. We started with what a carboxylic acid derivative was, addition elimination, which ones are the most reactive, and the 2 factors that go into that. Then we went over some mechanisms of some important ones. This chart, I think it's pretty helpful, so please take a picture of it, look over it a few times because it'll definitely help with your exam. And then here are some of the exceptions that we went over, and then those are the practice problems. Hope you guys learned something, and good luck for your exam. See you guys later.